In this first screencast on magnetostatics, what I'd like to get to is how to calculate magnetic fields. What we've looked at is the forces due to charges moving through magnetic fields, and we've talked about dipoles, so I want to back up and we'll review that a little bit. But in this screencast, what we want to do is how do you calculate magnetic fields for arbitrary current distributions, and then how can you cheat using Ampere's law? It's the magnetic equivalent of Gauss's law. But where we started with our little self-demos activity in class was just looking at many cases where we can use the Lorentz force just to figure out which direction the force is on a wire due to charges moving through it as those charges are moving through a magnetic field. And so in this wire above, something we didn't talk about in too much detail is we take the positive charge convention when we do these problems. So a positive charge I have here is moving to the right. If I wanted to instead, however, I could say, well, that's just the same as negative charges moving to the left. All right, so let's just do this quick Lorentz force problem. And here my magnetic field is in the y direction. That's going into the page. And if I'm looking at the convention of the positive charge, it's moving to the right. And if I'm looking at the negative charge, it's moving to the left. So just simply solving this here, this cross product, I'm going to get, in the positive case, it's a positive Q, and then it's going to be V x hat. I need to make a big X for a cross, perhaps, and then cross B y hat. Okay? And X cross Y, X hat cross Y hat is going to be Z hat. You can use your right hand rule here. If you point your fingers in the direction of the charge, you're going to curl them in the Y direction into the screen that you're looking at, and your thumb should be pointing up. And so what you'll get is you'll get Q, V, B, Z hat. Alright? What if we did it with a negative charge instead? That's equivalent to, I have my negative Q now, but it's moving in minus X direction, cross B, and I'm just going to get Q, V, B, Z. If you're doing an experiment like the Hall effect, that's actually how you can determine the charge carrier as the electron. This is going to matter. But in our case, whether we pick minus or plus, it doesn't really matter. And so we're just going to take the convention to be positive charges, like we did positive test charges in electrostatics. And pretty soon we're going to be talking about currents, and we want to sum up currents. And those currents, we're going to assume positive. If you want to say those are electrons instead, just have them move backwards. We're going to get the exact same results. Let's go over a dipole again real briefly, and then let's talk about how to calculate magnetic fields. So again, you got a lot of information out of physical systems that occur in lab, that occur in deep space, just from this Lorentz law right here. We can actually motivate a lot of interesting physical things. All right, dipoles, and then let's calculate some magnetic fields, or show you how to calculate magnetic fields using Biot-Savart and Ampere's law. On the screen, here's a picture of a magnetic dipole. This is actually close to, other than the crappy drawing, a perfect dipole. If you look on page 255 of Griffiths, he shows you the difference between a pure dipole, which looks more like this, and then a physical dipole. And note, you can see the difference between a physical magnetic dipole and a physical electric dipole. So in their approximations of being pure dipoles, they're exactly the same, but due to this total difference of how you make an electric dipole and how you make a magnetic dipole, the physical dipoles are different. And that's what we drew on the board just the other day. The base unit of magnetism is this basically this arrow or this north-south. So it's kind of unfair to talk about the field inside a magnetic dipole, and you can talk about that field inside an electric dipole because it's made up of two smaller bits, which is charge. And so what we did is we talked about how you could, if you had another a little bar magnet. Let's say we put a little bar magnet down here. If you like this interpretation, the Gilbert model here, and I put I arranged it so that it was north-south, you'd find that these would attract each other. But really, why are they attracting each other? Why does this north attract this south? It's really because this thing is thought of as a current loop. There's a current going around here, and if I look at the current here and the current here, and I look at the Lorentz force of those charges, how they act on the magnetic field produced by the other, I'm going to find that they attract. So I actually prefer this, and we talked about that. I actually prefer this model. It's more physical. And go ahead and check out page 255 to see the difference of a physical magnetic dipole and compare that with the electric. We'll be talking more about dipoles. We're going to be talking next about how to calculate magnetic field, and then eventually what we're going to be interested in is doing something like this. We're going to have a chunk of stuff, and it's going to have maybe randomly oriented magnetic dipoles, and we'll turn on a magnetic field now, and that's going to align these dipoles, which is going to produce a magnetic field analogous to polarization. So magnetization, which you've heard before and have thought about before probably, is going to be completely analogous mathematically and almost analogously conceptually to polarization for electric fields, which we just covered. We've already talked about how the base unit of of magnetism is a dipole, and then dipole can be thought of as a little current loop. So all magnetic fields arise from currents and the sum of different currents. And so this is very analogous to what we're about to do, like Coulomb's law for magnetism, and it's called Biot-Savart. And so what we did when we had electrostatics is we looked at line charges. And so we're going to have line currents. So here's a line current, which is kind of redundant in word, a line current. We're going to have surface currents. You can imagine there's a current on like a sheet here. And you can imagine that you have volume currents. There's currents that are going through an entire volume. And what we want is we're always going to be interested in I. The magnetic field is going to be related to I, and we can relate these to now K. K is the surface current density. And so I is the line current density. That's kind of redundant. And K is the surface current density, and J is the volume current density. And this is analogous to sigma and rho, like we had before, and then lambda again. All right. Now, what is kind of sneaky here is the dl that you're integrating over to get the total I is there's this little perpendicular symbol, and this is on Griffiths in pages 220 and 221. All right, so if I want to add up all the current through this sheet, and I know the surface current density, what I need to do is I'm basically adding up these little strips. All right, so the surface current is going this way. I should actually put an arrow there. The surface current in this one is maybe going this way along this sheet. And if I want to add up the total current on this sheet, and I know the surface current density, K, then all I have to do is add up strips. And this is the infinitesimal strip, dl. If I have a current going through a volume, this is this weird little sausage-looking thing. Griffiths has a similar picture on 221. What I can do is I can take a little cross-section, and this will correspond to tubes now, or they could be little boxes if you prefer. And all I really need to know is the cross-section in order to add up the entire current. If I know the volume current density, and I can take these little these little tubes here, I can add up all those tubes. And what matters here is the cross-section, and then I can get the total enclosed current. So it's a little weird because of the dimensionality. Our highest dimensionality for current is going to be area, not volume. But it's a volume current, and that's just because we start on lines, we don't start on little bits. All right, so if we already start on lines, we're going to up to surface and volume. We're interested in adding up how these lines of current add up total. All right, so if you want, you can think of like, look, if I add lots of little lines here, and I add up all those lines, I'm going to get total I. If I add up all the lines through this volume, I'm going to get total I. And one way to add up the lines in the volume is to add up these little tubes here, is to add up these little strips, and here you don't even have to. Okay, so we're going to be using I, and that's nice, and often that's what we want because it's some kind of circuit or some kind of wire, but you might have a surface current and you might have a volume current too. Here is the Biot-Savart law in all its ugly glory. If you notice, it's extremely similar to Coulomb's law. You have this R script squared, you have an R hat on top. If it is a line current, you integrate over dl, dA for the surface current, and d tau for the volume. And then there's just one extra nasty thing, and it's not terribly extra nasty, but we have now a cross product on top as well. So whenever you can avoid using Biot-Savart law, you should, just like you should always avoid using Coulomb's law for electrostatics. Like we've done before, we can take this R script hat and call that just R script over, or script R, so we get an R cubed down here and an R vector. Let's just do a sample, start out with a wire to show you how to set this up, do a volume, and then we'll move on to the easier version, Ampere's law. In the example I've set up here, what we have is this is supposed to be a loop of wire carrying a current I. and a constant current I. Let's actually write that down because it might not be constant. In fact, I could depend on the coordinate system, just like you don't necessarily have constant charge density. So let me rewrite that again. I'm going to call that I, and let me even write the vector here. It's going in the phi hat direction because it's going around. Okay, so I is going in the phi hat direction here. And what I'm interested in, what's the magnetic field at point P there. So here's the similar form to what you saw on the other screen, although I've written the r hat as the r script vector over r cubed. One r comes down, and r squared times r gives you r cubed on the bottom. This is the magnetic permeability, as opposed to what we had before in electric fields. We had the electric permittivity. Okay, and this is just based on the units that we're using. So this is an extremely similar problem to Coulomb's law. So what I need to do is I need to draw from the origin to some element of current that I'm integrating over. This says I'm integrating the prime again. That's where the current is, and the current is all over this loop. And so here's one little element where the current lives. And so from 0 to where some arbitrary element is, that's going to be my r prime. From 0 to my point, that's going to be r. And r script again is going to be r minus r prime. And it's going to go from the element where you're interested in integrating to the point. Alright, so let's write down those vectors. Once again, we're going to have to, if it's the symmetry of the system here, you can see it's cylindrical. We're going to have to translate into Cartesian before we integrate, because the unit vectors themselves might depend on the variables of integration of the system. Alright, so let's start with the vectors. Let's also define what dl prime is. So let's do this. We know that our script, we can do our fancy change color thing, is going to be r minus r prime. Alright, and then we know that, let's start with r. R in this case, I'm just going to call it, again, what's the symmetry? We're going to go cylindrical. So we have S, phi, and z. So this is going to be z naught prime, z hat. So no z prime, z hat. And then the r prime vector is just going to be, we're a distance a out. When we integrate around here, we're not going any more than a. So this one is just going to be confined to a s hat. And so let's move it over here. Our script vector is just going to be equal to z hat minus a s hat. And we know we're going to have to translate into Cartesian at some point, alright, because dl is going to depend on phi, and s hat depends on phi. So let's rewrite this. This is going to be z hat minus a cos phi prime x hat y prime. If you want to, we said before we could do this. We could put prime here just to remember that this is in the prime system. All right, so that's going to be a cos phi x hat plus an a sine phi prime y hat. Okay. You might be able to tell already that the length of that is just going to be the square root of z squared plus a squared. Why is that? That's because when we square these components, the sine squared plus the cosine squared is just going to pull out an a squared. Okay, so there are our lengths. You can also tell from the Pythagorean theorem, if you wish, instead. If this is length z and this is length a, no matter how we integrate, no matter where we are in the circle, that hypotenuse is always going to be z squared plus a squared. These are always good checks to do to make sure, right? If you do it the hard way, could you cheat by using the Pythagorean theorem or law of cosines? We don't need law of cosines because we have a right angle here. So this r length is always going to be z squared plus a squared. Cool. I'm going to clean the screen here, and then let's continue. On this screen, you'll see I rewrote the r script vector not in Cartesian components. So I used the Cartesian components to verify the length r, which we said we could also get from the Pythagorean theorem, right? How to get this length r. But sometimes it's more handy when we take the cross product to leave it how it was. and then we might have to convert again, okay? So you'll see down here, if I take I is in the phi hat direction, and if I'm going to go I, right, it's I cross some R, the first component is going to be I phi hat, maybe I'll just write that down. The first component is going to be I phi hat cross z hat, right? And all that is going to be plus a I phi hat minus a s hat. Now you can use your right-hand rule to find out the direction of each of these components. The unit vectors are perpendicular towards to each other, so they're just going to give me the other unit vector, but we have to be careful about sign. If I point my fingers in the phi hat direction and curl them up towards z hat, what I'll find is my thumb, the resultant, points in the s hat direction. So that first part there is just going to be I z s hat. Okay? Plus, let's go to the next one now. This one is going to go, again, I'm going to put my hands in the direction of phi hat. Phi hat changes depending where you're looking, but if I'm looking at my element here, I'm going to point my fingers in the direction of phi hat. And now what I'm going to do is I'm going to curl them in the direction of minus s hat, that would be inward. And I find that I'm left over with the z direction, the z hat direction. So then that would be plus I a z hat. Alright, let's clear another page to clean this up a little bit. Plugging in everything from the other screen, this is what I'm left with. I have now zs hat plus a z hat on the top. My dl, remember I'm integrating around this ring, and so it's going to have a constant radius a integrated over phi. And there's a hat there. That shouldn't be there. Let's just cross that out. That should have been a prime. Let's just make that a prime. There we go. Let's just pretend that's a big prime there. Okay, so there's one problem here. Now we, even though we converted back to our cylindrical system, we have an s hat here. We have to get rid of that and make that Cartesian now because we're going to integrate over phi prime. So we're going to rewrite that as, this is going to look a little ugly, and then when you see this, this is actually just going to cancel out. This one right here is going to cancel out, but let me write it out anyway. That's going to be equal to mu naught over 4 pi. And then it's going to be z, and that s hat component is going to be, let's get rid of that, it's going to be cos phi prime x hat plus sine phi prime y hat. Okay, then we're going to have plus az hat. And that whole thing is going to be times a d phi prime, that's integrated, a squared plus z squared to the 3/2. Okay, remember when you integrate the cosine, I didn't put my limits here. I'm going from 0 to 2 pi all the way around this ring here. And when I go all the way around, I'm going to get 0. The cosine starts and stops at the same value. So this part here is 0. Okay, and then the nice thing we can see about the phi integration here, nothing depends on phi that's left over. Do you see? So that part canceled out, so all I'm left with is a z hat over this, and none of these depend on phi. So this was actually a pretty simple one to solve. That's just going to be equal to, let me get my pen back, mu naught over 4 pi. Alright, the phi integration is going to give me a 2 pi. Times, I have an a and an a, so it's going to be an a squared. A squared just over a squared plus z squared to the 3/2. Okay, and that's going to be mu naught a squared over 2 a squared plus z squared to the 3/2. All right, very easy integration. So sometimes we're lucky. This is actually an example in Griffiths, and I don't like the way he does it. It's an example 5.6. What you should find is we get the same value. And I'm looking, and I forgot to carry an I. There should have been an I here the entire time, and an I out here the entire time. I is constant, and an I, and an I. Okay. Other than that, we got it. Okay. So if you look at Griffiths, example 5.6, we did it the rigorous way with R script and R hats, and not a geometrical cheat. He does an okay job, but again, he sets up this nice formalism and then doesn't use it. So you do every kind of Biot-Savart problem like this. Note we might have it integrated over a surface or a volume, and lucky you'll get to do that. I'm going to save Ampere's law for another screencast because this one's getting long. But for your homework, you have a wire. A square grid wire, very, very, very similar. Obviously, you won't use cylindrical symmetry.